So hello everyone again. This is lecture 6 part 2 of wave optics. In the last lecture I was explaining you the final discussion of Young's double slit experiment. What are the effects on interference fringes occurring if there is a, let's say, change in the source of light, or let's say there is a change in the lambda value, small d value, capital D value, etc. Today I will start from that last final discussion of interference fringes only, and then we will move on to new concept called as diffraction. What is diffraction, why was diffraction observed, etc. will be explained in that slides. So I am Sameer Lavankar, let us begin our discussion. So we have started with introduction, then we went to wavefront, Huygens principle known as nothing but wavefront explanation was being done in that part. Then in the third part I explained to you the refraction and the reflection laws of plane waves using Huygens principle, in which the concept of wavefront was being used to prove the reflection laws and refraction laws. In this we also understood the Snell's law. What is Snell's law of refraction? We also understood the concept of refraction of light, total internal reflection. Then we went on to coherent and incoherent addition of waves. What is coherent addition, what is incoherent addition, why was there a need of intensity being changing in the coherent and incoherent, why is only n lambda value being used for intensity to be maximum, why is n lambda by 2 or n plus 1 by 2 lambda being used for incoherent addition of waves. Then we understood a small concept of Doppler effect. I explained that complete concept using some of the diagrams, that what is happening if the source is being intact, what if it is moving in this direction, what is moving away from the source, etc. Doppler effect is also applicable in sound waves also, so I explained you using that concept. Finally we went down to the interference of light waves and Young's experiment. In this we are in the last stage of Young's experiment. I will try to explain the last concept again of monochromatic light so that it is clearly understood, and then we will move on to diffraction of light. Okay, so interference of light waves. So let me just go on to the last point only. Okay, so the question was that what is the effect on the interference fringes in a Young's double slit experiment. Please make sure the double slit experiment is being talked about here. So due to each of the following operations, so the final operation was being needed to be explained again. So it is saying that the monochromatic source is replaced by a source of white light. So what will happen, as we know that white light is a combination of different wavelengths. It is a combination of different wavelengths. It is a combination of different wavelengths. So what will happen if what does a monochromatic source means? Monochromatic source means it is a light of a single wavelength. So just let me explain to you. So it is nothing but it is a light of single wavelength. Okay. So the explanation is, I will try to explain it again. So what is happening here is the interference patterns due to the different component colors of white light overlap. So what will happen is, as it is a combination of different wavelengths, therefore everything will overlap at a point P, because the value of lambda is different for different wavelength, different colors, hence the value will overlap at different points in the screen. So now we are just taking a consequence of what will happen in different scenarios of value of x. So first of all let me revise you one of the concepts. So we know that when the path difference, let me write it here only. So when the path difference is equal to, let us say, lambda by 2. So if it is lambda by 2, then always there is a destructive interference. This is nothing but a scenario of destructive interference, and when destructive interference is happening, then the intensity is 0. So as white light is a combination of different wavelengths, so a color which is having, let us say, a supposedly value of lambda at any point of x, then the intensity due to that wavelength will be 0 at that point, but it is not for different case. So that example is being explained here. So we know that for blue light the wavelength is 4000 angstroms. It is 4000 angstroms, and similarly for red light it is 8000 angstroms. So what does it try to say is, what does the answers try to say? Let us say at some point, let us say that distance being told here is x, let us say this is at point O on the screen, let it, this is the point P. So this is the point P at which we need to find out what will be the color being visible here. So if the value of, let's say, the path difference is coming to be equal to, let's say I write this is lambda B, and let's say I write this is lambda R. So what it is saying is, if the value of lambda, if the value of path difference, let's say I write path difference as PD, if the value of path difference is equal to lambda B by 2, then what is happening is, for the blue color light the value of path difference is lambda by 2, hence the intensity of that light will be 0. Therefore at that point, when the path difference is 0, then at that point red color will be visible. Similarly, what will happen is, let us suppose, I will explain it here. Let us suppose that path difference is equal to lambda R by 2. So what is happening in this case, lambda R by 2, so lambda R by 2, again path difference of lambda by 2 is occurring, hence there will be destructive interference for red light, hence red light won't be observed. So because red light won't be observed, a blue light will be observed at that position. So what is this blue light, red light observing? So the fringe, the color of the fringes being observed, the color of the fringes being observed will be of different colors now. If the monochromatic light was being used, only a bright fringe and a dark fringe was being used depending on the color which the wavelength of the light source emits. But this time, because it is a white light is being used and it is a combination of different wavelength of lights, therefore this concept is need to be explained here. Okay. So the central bright fringe for different colors are at the same position, therefore the central fringe is white. So at the addition, so at this point, because there will be addition of every wave and every path difference will be same here, path difference will be 0 here, therefore path difference won't be 0, path difference will be constant here. So therefore at this point the value of central bright fringe will be a combination of all the wavelengths, hence it will be 0. But for a point P for which S2P minus S1P, S2P minus S1P is nothing but the path difference, which will be equal to lambda B by 2, where lambda B is nothing but 4000 Armstrongs, which represents the wavelength for the blue color. The blue component will be absent. So quite evident, I explained to you why the blue color will be absent, and because blue color is absent, the fringes will appear red in color. Similarly, for farther away where S2Q, so we are assuming a different point Q at which the path difference denoted by S2Q minus S1Q is equal to lambda B, which is equal to lambda R by 2. What is lambda R? Lambda R is nothing but the wavelength of the red color. It is around 8000 Armstrongs. The fringe will be predominantly blue. So again the blue red component at this point will be absent, and hence the fringe will appear blue in color. Thus the fringe closest on either side of the central bright fringe is red and farthest will appear blue. So near to the point, so if we need to calculate, let us say these are the, let me explain it here. Okay, I will try to make it more clear. Let us say I use a black color. Let us say this is the screen being observed. Do we have a white color here? So let us suppose, okay, we have a white color. So let us say this is the central fringe being explained here. Then as we go farther away, first of all there will be a blue color light. So let us suppose this. So thus the fringe closest on this side will be is red and the farthest will appear blue. So at the near point, let us suppose we are talking about this portion. So at this portion we can see a red fringe, then this portion also we can see a red fringe, then the intensity of that may differ, something like this. Let us suppose that this is lighter shade of this red color. Then after this what will happen is there will be a blue color intensity after farther difference. So then farther difference, blue color will be visible, then this blue color light will start fading, then this blue color light will start fading, and then after this more blue light will start fading. So there is change in the color. So somewhat not appropriately this, because there will be a change because there is combination of different wavelengths being happening, but somewhat the concept will be like this. So these will be the interference fringes being formed when there is a change in the monochromatic source to a white source of light. So this was the final explanation, this was the final conclusion I need to explain to you regarding all the concepts of interference of light waves and Young's experiment. So from this last data what we found out two different concepts. First was just a simple explanation of fringe width, that is beta is equal to lambda capital D by small d should be used. So this is the first concept, and second concept is we need to remember the satisfactory formula, that is capital S small s by capital S, small s by capital S should be less than capital D by lambda small d. So please make sure we need to satisfy these conditions, and after this condition is being satisfied, interference fringes will be formed, and similarly we need to remember this formula for width, which is equal to lambda capital D by small d. Small s by capital S is less than lambda by small d. Okay, and finally we explained to you complete concept of monochromatic source of light is being replaced by white source of light. So this is the end of interference. Let us move on to a new discussion of diffraction. So what is diffraction, how it is different from interference, etc. So let's, without any further waste of time, let's move on to diffraction now. So a beautiful concept, please look over this very carefully, you will find it interesting. So if we look clearly at the shadow cast by an opaque object close to the region of geometrical shadow, there are alternate dark and bright regions just like in interference. This happens due to the phenomena of diffraction. So let me explain what it is trying to say. So if we understood the light as a Descartes theory, that is particle theory, let me explain. So let us suppose this is the screen. This is the screen. So let us suppose this is the first slit and let us suppose this is the second slit. So if there is a single, let me denote the slit as S1, let me denote the slit as S2, and let me denote the light by a dark blue color. So if we understood the concept of light as a particle theory, it always moves in a straight line. If it is always moving in a straight line, then the path should be somewhat like this. There should be no deviation. Please assume that this line is straight, even if it is wavy somewhat a little, please assume that this line. So the path of light should always be like this only. Similarly, the path of light from this portion should always be like this only. But what, so what does it try to say is there will always be a dark, there will always be a shadow here. The shadow will be due to this portion. Shadow, let me write reason of shadow. Because there is obstruction of light due to this portion here, hence there will be a shadow, there should be a shadow here. But what does it happen in real life? What happens in real life is, let me make a different diagram again. So I used red color here. So this is the screen again for you. This is the screen. Let us suppose these are the slits being formed. The slit as S1, let me note the slit as S2. In real reason, what happens is, let me change the color to blue. What will happen is we can find the fringes being formed here. Fringes are being formed in this portion also, in this portion also. So why it is happening? If we understood the complete concept of light, if it is traveling in a straight line, there should be a shadow in this portion. But really what happens is there are fringes being formed in even this area, maybe a central dark fringe, so a central bright fringe, consecutive dark fringes, etc. So why is this happening? This is happening because light can't be understood or light can't be theorized using the concepts of particle theory. So why it is happening? If we understood the complete concept as wavelets, so if the wavelets are being explained like this, if the wavelets are being formed due to the fringe, due to the interference being happening, or due to a concept called as diffraction being happening, we can't find a shadow here. So this is the complete concept of diffraction. What happens actually is the light, when it passes through this portion, there are slit corners here. Let me explain it clearly. It tries to bend from this position. So there is a bending happening. So there is a bending happening in this portion, and hence there is no shadow available in this area. So this is the complete concept of why a wave theory is being required to explain the concept of light. So let us move on to our discussion now. This was just the explanation of why there is a need for the diffraction concept to come into picture. So if we look clearly at the shadow cast by an opaque object, so quite evident this is that opaque object here. So this is that opaque object. Okay, if you look clearly at a shadow cast by an opaque object close to the region of a geometrical shadow, there are alternate dark and bright fringes just like in interference. So there can be visible dark and bright fringes here. Let me write dark and bright fringes. So dark and bright fringes are available in this portion here. So again, moreover, so this happens. Why does it happen? This happens due to a phenomena called as diffraction of light. What is diffraction of light? Diffraction is a general characteristic exhibited by all types of waves, be it sound waves, light waves, water waves or matter waves. Since the wavelength of light is much smaller than the dimensions of most obstacles, we do not encounter diffraction effects of light in everyday observation. So what does it try to say is, what is diffraction? Diffraction is nothing but the bending of light at the corners due to, why does it happen? It happens only and only when the object through which the light bends is of the order of the wavelength of light. So So only and only diffraction is applicable when the obstacle through which it passes has the dimensions which are in the order of wavelength of light. It does not happen in all the scenarios. It is saying that why does not happen in everyday observations, because let us say if I take this pen, if I take this substance here, everything has a dimension size which is very greater than the wavelength of light. If the dimension through which if the bending is occurring is of the slits is of the order of wavelength of light, then there will be diffraction pattern observing, otherwise it will not be observed. So however, the finite resolution of our eye or of optical instruments such as telescopes or microscopes is limited due to the phenomena of diffraction. So why it is limited? Due to the phenomena of diffraction. This is just a theoretical concept which you should know, that finite resolution of our eye. What is finite resolution? I will try to explain it, because that concept is also we need to explain to you in the further slides. For now just explain this, that the finite resolution of our eye or of optical instruments such as telescopes or microscopes is limited due to the phenomena of diffraction. Indeed, the colors that you see when a CD is viewed is due to diffraction effect. So what is happening is, as you can see on the back of the CD, there are different rainbow colors being observed on the slide. So that observed is due to the diffraction occurring due to the light waves, and that rainbow color which you observe on a CD is also due to the diffraction effects only. So that is one of the simple example which you can see in your everyday life of diffraction. Okay, so now let us move on to a single slit experiment. What is the single slit experiment? What does it try to say? Please look over here carefully, very beautiful experiment. So in the discussion of Young's experiment, we stated that a single narrow slit acts as a new source from which light spreads out. So in the Young's experiment, used a single slit to use it as a source of light. What happens if we use that slit source of light to find out the interference fringes on a screen? So for this, first of all I will try to explain you what is happening here, then in the subsequent lectures or in the subsequent slides I will try to explain you whatever is written. So as you can see, these are the incoming waves. This is nothing but the light source or the sound source, as the case may be. For us it is light source here. So after this light source, as you can see that these are the graphs of light waves being formed. So every crest or every maximum is nothing but a bright fringe, and every down is nothing but a dark fringe. As you can see from the intensities also here, that it is a bright fringe, then it is followed by a dark fringe, hence a bright fringe. And also you can see that the intensities keep on decreasing. It is maximum at the central portion, but it keeps on decreasing at the later portions. The below diagram is required only and only when I try to explain you why it is happening, why is there a decrease as we go. So this was the concept I was trying to explain to you in the previous concept of double slit experiment. Even with the change in the path difference, the value of the intensity at every portion was constant, which is equal to I max or I0. But here when we try to move apart, the value of I decreases, keeps on decreasing as the path difference is being changed. Why does it change? It is simple explanation of this diagram being shown in the below portion. I will try to explain you this in the next slide. For now I will try to conclude the class here only. So in this class I tried to explain to you why a diffraction concept was important, why in real scenarios if we explain it using Descartes' theory of particle, then a shadow should be available here, but because a shadow is not available, a bending of light is occurring. What is bending of light? Bending of light is nothing but a diffraction phenomena occurring due to only and only when the obstacle through which the light passes has the wavelength which is similar or in the same order as that of the wavelength of light. So this is the complete concept of diffraction. I will try to move towards further why there is a difference in the interference fringes formed here, what is the difference between interference and diffraction as the case may be, and then this diffraction concept is completed. So for now let me stop it here only. Thank you.